Okay, enough with the technical background that we need. Now we can focus on the two problems for symmetry breaking that we encounter in the philosophical literature, Herman's puzzle and Baker's dilemma. Let's start with the first one. And let's read directly from a quotation that in which Herman explains the content of his puzzle. He says, a broken symmetry is not unitarily implementable, i.e. its action is not fully represented by a unitary, but how can this be, since Vignette's theorem has taught us that a symmetry in QM is represented by a unitary transformation, and I will tell you what these terms means. But so the puzzle is that on the one hand, symmetry breaking implies that the two representations pi and pi prime are not unitary equivalent, namely the symmetry is not unitary implementable. And on the other hand, however, the celebrated Vignette theorem that is taken to be like a standard theorem in quantum mechanics tells us that a quantum symmetry, even when it is broken, must be represented by some unitary operator. So let's look at this puzzle more in detail, and then I will tell you what the solution is, and then we'll move to the other dilemma. Okay. So we have the two representations before and after the symmetry is applied. Notice that an automorphism alpha, like a symmetry is said to be unitarily implementable in the state omega if there exists a unitary operator such that pi and pi prime are intertwined according to this relation by the given unitary operator. Equivalently, we say that the representation pi and pi prime are unitarily equivalent. So they're connected by a unitary operator. A stronger notion at the level of the algebra is that of the inner automorphism, according to which there is a unitary operator contained in the algebra that provides an explicit expression for our symmetry alpha. If this automorphism is inner, then the two representations pi and pi prime originated by the symmetry are unitary equivalent. Graphically, we can understand this idea as follows. Well, let me first tell you a bit more. Why is this relevant for the debate about broken, or the distinction between broken and broken symmetries? Well, as it turns out, if we have an unbroken symmetry, then the underlying, or the two representations pi and pi prime are unitary equivalent. Instead, if the two representations pi and pi prime are not unitary equivalent, then the symmetry is broken. That is to say, the ground state is not left invariant by the symmetry, and we can always find some observable for which the value of the state on that observable before the symmetry is different than the value after the symmetry is applied. Okay, so graphically we can understand the idea of unitary equivalence as follows. The symmetry can be expressed by a unitary here, and the two representations are unitarily equivalent. They can be connected by another unitary operator. Okay, if the symmetry is broken, instead, things are different. In particular, the symmetry cannot be inner, so there is no unitary operator that implements it, and also unitary equivalence fails. So in this way, we understand the first part of Herman's puzzle. What about the second part? Well, there is an important theorem due to Vignette that captures the content of a quantum symmetry. Now, the underlying idea is that in order to preserve the empirical content of quantum theory, then the symmetry alpha must preserve the inner product, which, if you know quantum mechanics, is usually taken to represent the transition probabilities. So a symmetry must preserve transition probabilities. And Vignette was able to show that any symmetry is actually implemented by a unitary operator, which W, which we can call Vignette unitary, that goes from one Hilbert space to the other, and preserves the inner product and therefore also the transition probabilities. Baker and Alverson in 2013 were able to show at the level of representation what they called a Vignette representation theorem that for every symmetry alpha, even when it is broken, there always exists a unique Vignette unitary that preserves the transition probabilities across the two representation pi and pi prime. Okay, so Herman says, Vignette theorem implies that every symmetry, even if it is broken, must be represented by a unitary operator. However, in the case of broken symmetries, we saw it before, the representations are not unitary equivalent. So the solution of the puzzle is actually this. So we have a quantum symmetry. We're back to that diagram. If unitary equivalence holds, we have this situation. However, if unitary equivalence is violated, and so we have a broken symmetry, then there is a unitary operator, a Vignette unitary that connects the two representations. However, it does so in such a way that unitary equivalence is now maintained, namely pi x is now sent to pi prime x. It is sent somewhere else in the representation pi prime, but not on the corresponding element. Okay, so we still have a unitary operator representing the symmetry, a Vignette unitary, but this is not a unitary operator that intertwines the two representations. And so Herman's puzzle that we saw before, and I'm just repeating what I wrote before, finds a solution exactly based on this fact. Okay, for any symmetry alpha, we can find a Vignette unitary W that represents the symmetry and preserves transition probabilities as it is required, even though the two representations are not unitarily equivalent. Okay, and of course we can see, and if you want I can come back later on to the slides, we can see its application in the case of the ferromagnet, okay, which is a case of broken symmetry. But due to the shortage of time available, let me go to the other philosophical problem, which is raised by a dilemma proposed by Dave Baker in 2011. And let me read from his quotation here. He says, the apparent dilemma that has to do with actually symmetry breaking brings together two separate threads in recent literature. One thread suggests that the existence of a symmetry is a mark of physical equivalence. The second thread suggests that physical equivalence is possible only in presence of unitary equivalence. In the example central to this paper, and the focus is in particular on the infinite spin chain and its spontaneous magnetization, then a symmetry can exist between representations without a unitary equivalence. So the conflict here is obvious. And to make it even more obvious, let me just provide the logical scheme of this dilemma, okay? The underlying condition that we learned from Herman's puzzle is that a symmetry, the existence of a symmetry, does not imply unitary equivalence. Broken symmetries are such that the two representations pi and pi prime are not unitary equivalent. And then the first horn of the dilemma says that a symmetry implies physical equivalence, and the second horn of the dilemma implies that physical equivalence implies unitary equivalence. So if we start with a symmetry, by the first horn, it implies physical equivalence, which in turn by the second horn implies unitary equivalence. However, that's in contrast with the statement 0 that we learned from Herman's puzzle. So we can have a symmetry without unitary equivalence. The solution of this dilemma, according to Baker, is that the second horn of the dilemma is actually false and it should be dropped. While the first horn, the first statement that a symmetry implies physical equivalence must be maintained. And this argument goes as follows. It provides an argument in favor of the first statement. According to him, if we take global space-time symmetries, they cannot relate different physical possibilities since they do not correspond to real changes of a system, but just a change of coordinates. And so in particular, there are no intrinsic properties that makes different space-time points ontologically distinct. And he claims that this condition in particular holds in for classical space-time symmetries. And we can formulate this condition, which is a metaphysical principle going under the name of no primitive identity, is that if we take two space-time points, x and x prime, being connected by a space-time symmetry alpha, then the corresponding states, omega x and omega x prime, must necessarily represent the same physical state. And arguably, or at least that's what Baker argues, no primitive identity would imply that distinct ground states, such as the two phases of a ferromagnet, omega plus, all spins up, and omega minus, all spins down, must be physically equivalent. So there's a problem with this claim that suppose that no primitive identity hold for classical space-time symmetries, which is not granted. But even supposing so, does it really extend to general quantum symmetries like the one we're considering here? And that's an open question on which I will return at the end of the talk. The motivation for dropping the second statement, namely to deny the physical equivalence implies unitary equivalence, for Baker goes along the following lines. So physically equivalent representations must preserve the empirical content of quantum theories. But what is the empirical content exactly? So by Vignette theorem, we learned any symmetry alpha will be implemented by a Vignette unitary, and therefore it preserves transition probabilities. Now, Baker, relying on the theorem he proved with Unsalvorson, claims that the empirical content is sort of entirely captured by transition probabilities. And if that's the case, then unitary equivalence is not necessary for physical equivalence, because even if unitary equivalence fails, but we have a symmetry, as in the case of a broken symmetry, then physical equivalence is guaranteed because transition probabilities are preserved. And so that's for him the reason to deny statement 2 and propose an alternative statement according to which physical equivalence does not imply unitary equivalence. Okay? And so that's what I just said. Now, I have concerns about this claim that will become more explicit when we deal with the case of ferromagnetism. Now, true enough, part of the empirical content of the theory is captured by transition probabilities. And so a symmetry should preserve the empirical content, and therefore it should preserve transition probabilities, but the empirical content is not entirely captured by transition probabilities. There are other conditions. In particular, we know that since the state before the symmetry was applied, omega, and after the symmetry is applied, omega prime, yeah? If the symmetry is broken, they are not the same, then not all the expectations values computed in the ground state will be preserved. By definition of a broken symmetry, or as a corollary of the definition of broken symmetries, there will be some observables in the original algebra whose expectation value is not the same if computed in the representations of the state omega and in the representation of the state omega prime. Okay, so
sorry,
I think that
we are 30
yeah?
minutes into the talk.
Okay, so I speed up.
Yeah, 10, 15 minutes more, that'll be okay.
Okay, okay.
Yeah.
All right, thank you. So I think Baker and Albertson criterion for physical equivalence is actually inadequate because it rules out the difference between expectation values computed in omega and omega prime, and actually these values should be part of the empirical content. Okay, so now let's see why. Let's illustrate this claim by focusing on the case of the magnetization of a quantum spin chain. So for Baker, notwithstanding the fact that we have spontaneous symmetry breaking, the unitary inequivalent representation pi prime and pi minus must be physically equivalent. Otherwise, we would also violate the metaphysical principle of no primitive identity. Now, the problem is, are these the representations pi prime and pi minus physically equivalent just because the transition probabilities are preserved under the flip-flop symmetry alpha plus minus? And more in general, is the existence of a symmetry really sufficient to establish physical equivalence even when the symmetry is a broken one? Obviously, these are rhetorical questions because the answer, according to me, as you already understood, is no. So let's look at why I think, the solution to Baker's dilemma is actually to deny the first statement, namely the symmetries imply physical equivalence, which instead he would like to maintain. Now, in general, whether two representations are physical equivalence depends on the type of states we're considering. In the case of a ferromagnet, omega plus and omega minus corresponding to all spins up or down respectively are equilibrium Gibbs states, in which in particular the magnetization observable is dispersion free. This can be seen in the algebraic framework by looking at KMS states. We don't need to go into that. But the fact that omega plus and omega minus are equilibrium Gibbs states enables us to represent through them thermodynamical phases. And necessarily, these thermodynamical phases are different and physically inequivalent because they represent distinct phases. In particular, they're disjoint, as I will tell you in the next slide. And also they can form a mixture representing the coexistence between these phases at the same time, okay? And so based on these two features, these two properties, the corresponding representations must be physically inequivalent. So let's look at the first property. Here we need a preliminary notion, which is that of the volume of a state, which is the set of all possible states, all states that are possible relative to the given state. Now, if we look at the state all spins up and the state all spins down when the magnetic field is equal to 0 at a given inverse temperature, they actually prove to be disjoint in the sense that their folia have an empty intersection. So there is no state which is possible relative to each one of omega plus and omega minus. So in particular, omega plus is impossible with respect to omega minus and vice versa. And in fact, we can define distinct magnetization observables in the representation pi plus and pi minus that will give different values, plus minus and minus one, sorry, plus one and minus one respectively. In particular, the value of the magnetization observables in the volume of omega plus will be different than its value in the volume of omega minus. That's the reason why these two thermodynamical phases are actually empirically distinct. Also, and here I'm going to the second last slide, the two states, the two phases can actually form a well-defined, mathematically and physically well-defined mixture, which has this form. And if we start with this mixed state, which indicates the mutual coexistence of the two phases, then we can reconstruct each phases independently. Okay. Now, in particular, we should think about this mixture of omega plus and omega minus as a more mundane case, as the coexistence of two states of matter, for instance, ice and water. We know that they can coexist in the same state of affair in the world, and that's exactly the same situation, yeah, at the level of quantum theory. We can define a mixed state in which both phases coexist, and therefore they must be physically inequivalent. Otherwise, the mixture will not make any physical sense. Okay, so maybe last point. I denied the symmetry implies physical equivalence. Remember that according to Baker, the reason to maintain this implication was no primitive identity. So why we can deny this statement without violating no primitive identity? For three simple reasons. First of all, quantum statistical mechanics makes no direct connection with space-time, and Baker so the algebra of observables is simply defined in the R3 Euclidean space rather than in space-time, and no primitive identity as formulated by Baker only had to do with space-time symmetries. The only symmetries we're considering here are translations, okay, along this axis. And actually, if there is an axiom of the theory that tells us that this symmetry is unbroken. Last but not least, the flip-flop symmetry we're considering that map the up state into the down state is not a space-time symmetry at all. In particular, it doesn't map from one point in space into another. It just flips the spin from up to down or vice versa while staying in the same point. So no primitive identity does not apply here. And yeah,
sorry for the second interruption. We just knew that the next speaker won't be able to join us. So
okay.
We have, I'm so sorry, but we just knew.
No worries.
Okay, thank you.
I'm happy to go on. Yeah, as I'm in the last slide, the conclusion. So let me summarize the content of the talk, and then you're free to throw apples or oranges at me as a protest. So Now, Baker's dilemma, just as Herman's puzzle, philosophical problems whose solution enables us to better understand the concept of a broken symmetry. In particular, Baker's dilemma raises some important questions about the relation of symmetries, unitary equivalence, and physical equivalence. I believe that, true enough, we can establish general relations between symmetry and unitary equivalence at a mathematical level, but any question concerning physical equivalence should be settled on a case-by-case basis. So we might have different answers about whether two representations are physically inequivalent or not, depending on the physical scenario we are interested in. In quantum field theory, we might have different answers, but in the case of quantum statistical mechanics, and in particular the magnetization of a ferromagnet model as an infinite spins chain, then the ground states that we're considering, corresponding to all spins up or all spins down, respectively, represent empirically distinct thermodynamical phases. They have different empirical content, and moreover, they can coexist in the same mixed state. And this, I believe, is an indication that their representations are physically inequivalent, notwithstanding Baker's argument and his appeal to no primitive identity and the other arguments he puts forward. So the general moral we can draw from this case study is that the presence of a symmetry, especially in the case in which the symmetry is a broken one, is not at all sufficient to assure physical equivalence. In fact, in the case of a ferromagnet, the two phases are physically inequivalent. And that's my conclusion and the end of my presentation. Thanks for the attention.
Thank you so much, Giovanni. We didn't know that the next speaker was not going to join us. Yeah, well, but here we are. We have a few more minutes then for the Q&A. Yeah, feel free to raise your hands or write down the question. Okay.
Yes, Sam, I can see you.
Sam.
So here's a really deceptively simple question for you, Giovanni. What does it mean to say that two states are physically equivalent?
That they are physically equivalent?
Yeah.
Well, I would say, I don't know, usually if you take cases of unitary equivalence, could be, I don't know, so in the case in which a symmetry is not broken, then the symmetry is supposed.
I mean, just setting aside issues about symmetries or quantum theory or so on, because one of the questions that you're interested in asking about is the relationship between symmetries and physical equivalence. So I would have thought, right, first we need to understand what physical equivalence is, and then we can decide whether or not symmetries.
Well, you see, let me. Okay, it's very difficult, I think, to give an exhaustive answer to the question, what is physical
yeah, that's why it's a deceptively simple question.
Yeah, but we can list some of the necessary conditions for physical equivalence. Certainly, one is that, certainly, I mean, we should require that the empirical content of each state is preserved. Now, if we're dealing with a symmetry, certainly the transition probability is preserved, but I think also it should be the case that the expectation value, this very same observable when computed in the untransformed and the transformed ground state should be equal. If we take expectation values to tell us something about the empirical content of the theory. And so this condition, which is actually violated in the case of broken symmetries, I think it should be satisfied in the case in which we have physical equivalence, which is obviously not the case for symmetry breaking.
Right. Although, I mean, consider the following sort of argument, right? In your definition of symmetry, you gave that it consists of a pair of maps, one of which acts on the algebra of observables and another which acts on the states. So let's forget that we have even a case of broken symmetry. Let's just consider some situation that has some state, and we consider an operation, right, that changes, say, the
expectation value.
That it's, yeah, that it'll do something like it takes the operators that ask of a particular site on the magnet, are you spin up, and maps them to the operators, right, that say, are you spin down?
Okay, let me take the picture. This. Okay.
Yeah. So in this sort of situation, we've got a mapping of the algebra of observables that takes the for instance take the it would let the states remain invariant, but it would map the magnetization up values to down values. It's essentially just switching the labels, right?
Well, no, but you don't have that kind of transformation, and you don't have it because the two states are so to speak impossible with respect to each other. So
but we're not changing the states, we're only changing the observables, right? So
yeah, but the problem is that observables are state dependent. Let's see if I wrote it here. In order to build, where is it? In order to build a magnetization observable, I know this is awful looking, a lot of formalism. This magnetization observable is actually defined in the representation induced by a given state.
mm-hmm.
So in particular, we will have to take as, so if it is, so we can only define this magnetization for a given state. And as I wrote down here, so if you define the magnetization observable with respect to omega plus, this guy, the resulting magnetization observable, will not be defined for in the representation of omega minus.
We agree about that. I think maybe I need to just use a simpler example. So
okay,
the sort of thing that I have in mind is that in the mathematics, there is we would represent like up and down and so on by numerical values like +1 or -1. But there's nothing in those numerical values which tell us this is up or this is down.
No,
right?
Let's say that there is a distinction which is maintained depending on how we conventionally fix
Good.
up or down. So
Yeah,
once the
yeah.
convention
And when
direction
I'm
is
asked,
up,
good, very good. Yeah. So what I'm asking about is like, how does that convention interact with the notion of physical equivalence, right? Given that we have these necessary criteria for physical equivalence
right.
that involve transition probabilities and expectation values, but those refer to these conventions, right? Given
Right.
that, like, does that mean that the criteria on your view, does that mean that the criteria for physical equivalence involve conventions as well? Or is there something else to be said about these sorts of cases?
I think, I would say that how you fix the terms conventionally doesn't have much to do with physics. It's in fact a pure convention that one poses, but then the distinction itself between up and down, or down and up, depending on how the convention goes, is a physical matter. Yeah, and something that it's perhaps akin to the era of time. They convention about past and future, but once we fix it, but the two things are different. The two entities are different, past and future. Now, if future is what it goes in, if you have the arrow time on the right, say, instead of on the left, it's more of your conventional decision. And yes, something similar. Up, we can conventionally decide what's up, or what's down, but the two things are always distinct. So whatever convention you take, the distinction persists, and this distinction is what has physical meaning. So there is a physical difference between the two cases, just as between past and future, there is a difference. But what you call past or future or up and down really depends on your convention.
Right. I think we agree about that.
Yeah, but we always agree, Simon. But
I don't want to take up too much more time with this line of questioning. If other people have questions, Giovanni and I could talk all day if we need to.
Yeah, but thanks also for putting your finger on some very important point that I perhaps needed to clarify in the talk, and now you gave me the opportunity to do so.
Thank you. Thanks, Sam. Anyone else? No.
Okay.
Yeah.
I would be happy to keep hearing the discussion between Sam and Giovanni if you want to continue.
Yeah, but you will also hear this discussion in Milan when Sam will visit us in the spring for the conference. But this is not to say that I'm not happy to continue now. I mean, it's really up to you.
Okay. Yeah, well, we have a couple of more minutes in case you want to make a clarification point, or otherwise we can, formally end the talk now and then continue talking for a few more minutes.
What's your preference, Giovanni?
If you have a question that I can answer in 2 minutes, I'm happy to go with that.
Okay. Yeah. Okay, then let's formally end the talk here, and we continue talking, like after the talk. So thank you so much, Giovanni, for your presentation.
Sure.
Thanks.
Thank you. And next time, hopefully, we'll be in presence, so we can, and in Spanish, so we can.
Yeah, your Spanish is very good.
Thank you. I have a good trainer, Tom.
Yeah. Yeah.
Okay. Thank you all then, and see you soon.
Gracias, Giovanni.
Gracias a
Yeah,
ustedes,
thank
a todos. Sí.
Gracias, gracias. And the next talk is at 10:30. So maybe I'll see you then. Thank you.
Okay, thanks.
Bye-bye.
By the way, Sam, sorry yesterday I couldn't go to your talk. I was traveling to
Don't worry about it.
Vienna
It's
from
okay.
Milan, so